In the last few classes, we were discussing about representations for context-free languages. We saw that there is a grammar representation using context-free grammar, and also there is an automata representation using push down automata. And now we are going to prove that push down automata, when we say push down automata, we mean non-deterministic push down automata. So PDA and context-free grammars are equivalent in power for representing languages, and that is the topic that we are going to discuss in this lecture and maybe in 2 more lectures. The topic for today is equivalence of context-free grammar and push down automata. We shall prove that CFG and PDA are equivalent. And this is the theorem introduced by Chomsky, Ivy and Schurzenberger in 1962. And the theorem says the class of languages definable by context-free grammars and push down automata coincide. So they both represent the same class of languages, namely context-free languages. And the proof has got 2 parts, and we shall prove that by 2 claims. Claim 1: given a context-free grammar G, we can obtain a push down automaton induced by G such that the language of the constructed automaton and the language of the given grammar are same. So we shall discuss a procedure to construct a push down automaton from a given context-free grammar. Claim 2 is the other direction. Given a push down automaton A, we can obtain an induced context-free grammar GA such that the obtained grammar and the given automaton represent the same language. And proof of claim 1 is relatively easy, which we shall do today, and we may need 2 lectures to prove claim 2. Now let us proceed and try to prove claim 1, that is, for every context-free grammar we can construct an equivalent push down automaton. So we are going to develop a procedure or an algorithm for converting a CFG into a PDA. We can try to understand the process by an illustrative example. Here is a context-free grammar for this language, and the construction that we are going to discuss is going to use Grayback normal form. This grammar is not in Grayback normal form. You can obtain an equivalent grammar in Grayback normal form. And here note that every production starts with a non-terminal, and in the RHS other than the non-terminal everything else is variables or string of variables. Here it is true, here also. Here after the non-terminal, terminal simple, there are non-variables or nothing is there. So this is in Grayback normal form. And now you can see that they are equivalent except for the null string. Here the language includes null string, which is not permissible in a GNF grammar. Now LMD stands for leftmost derivation. Now look at the leftmost derivation for AQ BQ. This is an unambiguous grammar, so you can have only one leftmost derivation, and here is how it goes. If you number the productions like 1, 2 and 3, two productions are there for the symbol capital S, one with RHS this and the other one with RHS this, and a production for B. Now you know that you have to start your derivation with the start simple, and suppose I apply production number 1, this is what I am getting. And here to replace this capital S, I am going to again apply production number 1, this is what I replace this S. Again production number 1, I will replace this S with the A. So this time I am applying production number 2. What is it? AB. So this S is getting replaced with small a capital B. Now the leftmost simple is capital B. Apply production number 3. I will get a B here. And now again you apply production number 3 on this capital B. And finally again 3. So it is easy to see this derivation, and question here is, can we simulate the leftmost derivation, say for AQ BQ, with a push down automaton? Answer is yes. How? The answer to this question will give you an algorithm for CFG to PDA conversion. So this is the idea. Use a single state push down automaton induced by this grammar. Grammar is assumed to be in GNF. So we are going to construct a single state push down automaton which can simulate the leftmost derivation of all the strings in the language of the grammar. So what we will be doing is, if you look at an arbitrary stage during the derivation at this stage, and what is done till now, starting from the start simple of the grammar, we already have derived a cube, and this is the sentential form that you have. The next simple for which you have to apply a production is capital B. So we will be trying to get a PDA such that when it wants to simulate a derivation, you know that the PDA will take the input in the input tape. So whatever be the part of the string which is already derived in the leftmost derivation will be already read by the corresponding automaton, single state. So the read head will be pointing to the next input simple, that is the first B, and whatever be the string of variables in the current sentential form, that will be the content of the stack. This is what we are going to do. So at any point of time, whatever be the string derived from grayback normal form, you know that you will have a terminal simple as the first simple in the RHS. So you know which one you can apply. If the next simple to be generated is small a, then you can apply any one of these. So whatever be the part of the string derived so far in the automaton that we are going to construct, that part will be already read by the automaton. So whatever be the next simple after this, the read head will be pointing to that, and whatever be the string of variables following that string derived, that will be the content of the stack. And now you note that in the derivation, capital B is the next variable for which you have to apply a production, and in the automaton, and that will be the topmost simple on the stack. So basically the variables of the grammar is going to be the stack alphabet of the automaton, and that is what we observe. Now with that basic information, we can try to develop an idea using the same example. This is that grammar. Now we will consider the leftmost derivation in this box, and we will try to represent the automaton's state or configuration here. And to start with, capital S is the start simple. So the derivation starts with capital S. And if you recall the idea that we discussed in the previous slide, whatever be the next variable for which we have to apply a production, that will be the top of stack symbol. So this is what we wanted. So S is the next symbol for which we need to apply a production. So that must be the topmost symbol on the stack. So to start with, the automaton will have the start symbol of the grammar as the top of stack symbol, and recall that all the variables here is going to be stack alphabets for the automaton, and not that nothing is derived in the grammar or in a derivation. So the read head is pointing to the first symbol. Only a single state, so that doesn't matter. Now suppose you apply production number 1, this is what you get. Now can you tell me how will you simulate that in the automaton? So here what exactly you need is read head to be positioned to the next, because you already generated small a, and stack content should be SB. SB should be the stack content, and the state is same. That is what you need. And you can easily observe that this is what the transition function you need. If you are in state Q, if you are reading small a, and if capital S is on top of stack, remain in that state. That is the only way. Replace this capital S with SB, and this is what you are going to do. So not that in this case, from this part, this string you already have derived small a, so the read head is pointing to the next symbol, the second a, and whatever be the remaining string of variables, that will be on the stack. This is what we need. And if you look at the relationship between this production and the transition function that you need in the automaton, then almost the algorithm is done. You can see that always the state is Q, it doesn't matter, and whatever be the first terminal symbol of that production, that is going to be the next input alphabet. Okay, because you are applying that production means like you are reading that input. So that this must be the next input symbol, and top of stack symbol must be the LHS of the production. Okay, it must be the LHS. And what is the RHS? The state is Q, no doubt, and whatever be the string of variables after the first terminal symbol, that will be the string going to the stack. Okay, now when you proceed, it will be clear. So what are you doing here? Now you applied the production 1 again, So for which we already have a transition. So what you do, it's again the same thing, you apply this transition. So you are saying that you remain in the state Q, replace this S with SB. So this is what you are getting. Again in the derivation you apply production number 1, for which there is already a transition. You apply that, this is what's going to happen. Okay. Now see, now you applied production number 2. According to the logic, what is the transition that you need? Production number 2 is this. So that means if you are in the state Q, if A is the next input simple and S is on the top of the stack, what you do is you replace that stack top with the variable B is what it is saying. That is, Q is the only state, A is the next input simple, top of stack symbol is capital S. In the RHS, state is saying what you push in is this string or variable alone, capital B. So if you apply that, what you are getting? QAS, this is the case you set, you apply, you stay back in Q and replace this S with capital B. Okay, that's what you do. And not that the machine that you are getting is non-deterministic, any of these two applies, assume that you are applying this. Now suppose in the derivation you are applying production number 3. Okay, so what is the corresponding transition you need here? Q, next input symbol is B, top of stack symbol is capital B. Okay, so LHS is QBB. What is the RHS? The state is Q. You are not going to push anything because after the terminal symbol nothing is there. So it is epsilon. So it's very mechanical and very easy to get that transition. And if you apply the transition, what is happening? You read this simple and take off this capital B. And the same transition can be applied in this state, and by corresponding to the application of 3 again. So what you do is you do this transition, and in the derivation, not that we are applying 3 again, so you have to apply this transition again. So this is what we are getting. Okay, I hope you remember, and this is what we did in the previous slide. This is the sequence of sentential forms that we derived, and this is the sequence of configurations of the push down automaton. Configuration means the current state, the remaining part of the input, and content of the stack. To start with, the entire input is to be read. Q is the only state and only the start symbol on the stack. Likewise, it progresses and you can verify offline. Now, if you see, you can see that at every stage, whatever be the string already derived in the derivation process, the content of the tape or the read head will be pointing to the next symbol after this, which is BBB is what is the remaining part of the input, or the read head is pointing to this B. And this is what we observed. So to start with, the entire input to be read, and capital S is the only symbol on the stack. So that needs to be the bottom symbol. The bottom symbol for this construction needs to be the start symbol of the grammar. And when you finish, the input is completely finished and the stack is empty. So you are going to accept by stack empty acceptance. Single state PDA simulating leftmost derivation. We can try to generalize what we did. Suppose you have a sentential form like this derived from the previous language, and this could be then a corresponding configuration. AA is already derived, so the read head is positioned at the next input symbol and the stack content is XYY. Now recall what we did to get a transition function from a production. Do you remember it? The only state is Q. From the state Q, if you are reading the input symbol small a and if capital X on the top of stack, then what do? You remain in that state and push in this string to the stack is what you need. That is, if you are in the only state Q and if you are reading the input symbol A and if capital X is on top of stack, then you replace the top of stack symbol with the string y1, y2, etc., yn. Okay, this is a straightforward approach now to follow, and it is a reversible construction as well. Suppose you have a transition rule like this, then you can write this production. That is, variable is this, input symbol, in the RHS the first terminal symbol is this, which is followed by this string. This is what you can easily write. Okay, that we will do in the next lecture. Okay, now we can try to formally define the PDA induced by a context-free grammar in Grayback normal form. So given a grammar, we are going to construct an automaton, push down automaton induced by the grammar with the same language as that of the grammar. Without loss of generality, we are assuming that the grammar is in Grayback normal form and hence productions are of this kind. A variable in the LHS going to a terminal followed by a string of variables. Okay, so what is the grammar? Grammar is, what is the push down automaton? Only one state, you call it as Q, and the input alphabet is same as the terminal symbols in the grammar, the same set. And what is variables? Variables are going to become the stack alphabets. Okay, this is the stack alphabet. I think we called it gamma. If you want, you can call it gamma, but it is the stack alphabet, the set of variables of the grammar. Only one state, so definitely that is going to be the start state. Then the bottom of stack symbol is the start symbol of the grammar that we already observed. It remains us to define the transition function, which we already know what to be done. If there is a production of this kind, x going to small a followed by a string of variables, then what is the corresponding transition you need? QAX is what you need in the LHS. Q is the only state, A is the next input symbol, and the LHS variable is going to be the top of stack symbol. What is the RHS? The only state, and the string to go into the stack is whatever string of variables is there after the first terminal symbol in the RHS of that production. So this is what we observed, and we can prove that the construction is correct, it is sound and complete. The language represented by the automaton is precisely the language represented by the grammar. There is a typing mistake, I will correct it. It should be A subscript G and this should be G, like this. With this, we are coming to the last slide, where I am giving you an exercise problem for you to practice and understand how this algorithm works. It's very important to try such an example to see whether you got that process or not. It is not at all a difficult process. It's a very straightforward, simple to follow process. Please apply it and see what kind of a push down automaton you are getting, and also show the computation on that automaton for this input string. Today we looked at the Chomsky-Abbe-Schurzenberger theorem, which claims that context-free grammars and push-down automata are equivalent in power for representing languages. There are two parts for the proof. One is a construction which can be applied to generate an equivalent push-down automaton from a given context-free grammar, and that is what we did today. So it remains us to go for the other side of the proof, where we need to get a construction for getting a context-free grammar from a push-down automaton. That we shall do in the next two lectures. Thank you.